Madin 2000 is a leading rotor dynamics software developed by Delta.js. In this video, we show its use for the nonlinear lateral analysis of an unstable system, a turbocharger supported on full floating ring bearings. Nonlinear analyses are carried out when the amplitude of the rotor displacement at the bearing is big, which can happen when the applied dynamic forces are big or when the system is unstable. In the present case, the system is unstable because of the very low bearing loads. Here is the model of the automotive turbocharger rotor that we are going to analyze. It consists of the compressor impeller, the turbine impeller, and the shaft, which is supported by two radial bearings. In this example, the bearings are full floating ring bearings. We are going to see how to model this type of bearings in Madin 2000. Here is the interface for floating ring bearings. The geometry of the inner and outer oil films is defined here. Here is the geometry of the inner bearing. Let's look at the linear bearing data. We can see here that the bearing specific load is very low. Here are the linear bearing coefficients of the inner bearing. And here the nonlinear bearing data of the inner bearing. It consists of two components. One component due to the journal rotation, which is defined by the Sommerfeld number and the force angle, and one component due to the journal velocity, which is defined by dimensionless damping coefficients. This is a plot of the force component due to the rotation of the shaft. The field of the force is shown as a function of the shaft position, which is defined by the relative eccentricity and angular position of the journal in the bearing clearance. And this is a plot of the component due to the velocity of the shaft. The outer bearing is modeled in the same way as the inner bearing. In this example, the ring is free to rotate. The speed of the ring is automatically calculated from the shaft speed and the viscosity of the inner and outer fluid films. In this analysis, the thermal expansion of the ring is taken into account and the clearances vary with the speed. Note that it is also possible to model bearings with semi-floating rings, also called squeeze film dampers. Here is a plot of the clearances as a function of speed. Here the temperatures in the shaft, ring and casing. And here the ring speed ratio. Now let's look at the results of the linear analysis. According to the Campbell diagram, three modes are unstable. One can see that the damping ratio of modes 1, 2, and 5 is negative. Since the system is linearly unstable, a nonlinear transient analysis is carried out in order to determine the limit cycle of the system, which is reached when the vibration stabilizes at a certain amplitude. In such a case, the orbit of the vibration has synchronous as well as subsynchronous components. First, a load case is defined. Here, a run-up with unbalance is simulated. This is the distribution of the unbalance in the rotor. And this is the run-up function. The rotor accelerates from 20% up to 100% of its nominal speed in 1 second. For the post-processing of the results, several kinds of plots are available. One can plot the absolute displacement of the shaft relative to the floating ring, and the displacement of the ring itself. Here we are going to have a look at the vibration at the compressor impeller. Spectral analyses are possible. One can do either waterfall plots or spectrogram plots. This is the spectrogram plot in the horizontal direction. One can see the synchronous vibration due to the unbalance and the non-synchronous vibration caused by the unstable modes. For example, this line corresponds to the outer oil whirl. It is also possible to do orbit plots at different instants. The shape of the deformed rotor can be plotted at any desired speed. One can also plot the forces in the bearings. Many additional features facilitate the nonlinear simulation of complex lateral models. Are you interested in our advanced rotordynamic software? Feel free to contact us for more information.